I would like to thank Sophion Bioscience for organizing this really exciting event, and also thank the advisory committee for inviting me. I'm going to talk about the gating and the modulation of KSynQ1 channels. This is just the disclosure. So IKS channel, that is very important in the heart. This is a ventricular action potential. IKS current will turn on very slowly. That's why it's called IKS, slow. And then, but once it's turned on at the end of the action potential, it is very important to terminate action potential for the next heartbeat. IKS channel is formed by the voltage-gated potassium channel, KSynQ1 alpha subunit, and then the regulatory KSynE1, which was nicely introduced by Koichi already. KSynQ1 channel is a canonical voltage-dependent channel. That means that it has a voltage sensor, has a pore in the membrane, and also it has this so-called domain swapping structure. But what's different from the canonical voltage-dependent channel, KSynQ1 channel has intracellular domain. It binds to comodulin. So 4 subunits, each subunit will bind to 1 comodulin. And also it binds to PIP2 in 2 places, but I'm going to talk about the 1 PIP2 that is bound in the voltage sensor domain. Okay, KSynQ1 channel, if you express it itself, it can form the potassium channel. The current is quite robust, but if you co-express with the KSynE1, the channel property becomes very different. And that is very important for the cardiac function for IKS channel. It becomes much slower when it co-expresses. And also, it shows that the voltage dependence of the conductance is shifted to more positive voltages, and it changes also the ion permeability. So it basically, once you co-express with KSynE1, the channel becomes to a different channel. Why? So that was the question many years ago, and we solved we did the experiment and published in 2004, try to address this question. So we used the voltage clamp fluorometry, which has been described by many speakers before me. So all I want to say is that we make a fluorescence label at the S3, S4 this loop, so that it can monitor the voltage sensor movement, and the fluorescence monitors voltage sensor movement, and then the current from the 2 electrode voltage clamp will just monitor the pore opening, so that we can see that the voltage sensor activation and pore opening. And in both cases, voltage sensor activation has 2 components, with a fast component and a very slow component afterwards. And then the pore opening also has these 2 components. And when we plot the voltage dependence of those fluorescence, and then you can see that the fluorescence, this is a voltage dependence of fluorescence signal, and it can be fitted by 2 components, F1 and F2. So all these data to show is that the voltage dependent activation of this channel, KSynQ1, has 2 steps. And the 2 steps, you have this voltage sensor activation from the resting step to the intermediate step, and then from intermediate step to the fully activated step. In both steps, we see that the channel open. See, this is F1 step, channel already opens. So this is GV curve, and then it remains open at the F2 step, at this step, so that the channel can open at the intermediate state called this is IO state, and then it can also activate when the voltage sensor is at fully active state. So this is the AO state. So the channel has 2 states to open, and so in order to confirm that 2 open states, we try to make mutations to lock the channel, to arrest the channel in those two different open states. So what we did was to use S4. So you can see that S4 has 3 positive charges that moves during activation. And when it moves, we found that it interacts with a negative charge in the S2 segment. So this is the, during this normal activation. So what we did was to make mutations, a double charge reversal mutation. And so that the double charge reversal mutation would arrest the S4 into this intermediate state, and we found that the channel is constitutively open. And then we also made another mutation with this S4, the number 4 arginine, and then make this double charge reversal mutation, and it can arrest it in the activated state. And then we can see that the channel also opens, so that you have the intermediate open and fully activated open. So these 2 states, we did those mutations without knowing the structure, but later on the structure was solved by Jisun and McKinnon, Rad-McKinnon, on the fully active states, and you can see that this R4 is interacting with this E160, and this is where we lock them into the fully active state, and then we collaborated with Chuck Sanders' lab in Vanderbilt University, and they resolved a structure using NMR and found that the R2 is interacting with this E1, and this is the intermediate state. So when we lock them into the intermediate state and fully active state, channel do open. We do see 2 open states. And then we co-express the casein E1 with these constructs. And so here is the wild type channel. Casein E1 is slowly activating. But when we use this locked in the intermediate state, co-expressed with casein E1, there's no current. The casein E1 completely suppresses the intermediate open state. And then if you co-express casein E1 with this fully activated state, and the channel becomes more activated, so that what casein E1 does is simply suppresses the intermediate open state, but it enhances activated open state. And so it turns out that the intermediate open state and the fully active open state have very different properties. They act like 2 different channels. The intermediate open state has the ion selectivity that is different from the fully active state. And the casein Q1 channel, without casein E1, is predominantly intermediate open state. And then when it co-expresses with casein E1, it becomes completely just the activated open state, so that you have 2 open states with and without the casein E1, so that the channel looks like it's completely different. So what I try to say, this is just a kind of review, what the old data, that means that the 2 open states in these channels are very important for their electrophysiological function in the heart, because you need to have such a slow activation with the casein E1. All right, now, what does happen to the channel from the intermediate state to activated state? What are the structural basis for those? Okay, so right around like 2020, Jisun and Rad-McKinnon solved this cryo-EM structure of casein Q1 in the absence of PIP2 and in the presence of PIP2. So what they found was that this comodulin would bind to the intracellular alpha helices HA and HB. So this helix, HA, is the extension of S6. But when there is no PIP2 bond, so that the alpha helix is broken here, and then there is a band of this helix, so that which allows the signal of the comodulin to interact with the voltage sensor domain of the channel. So we call this a band structure. And then when there is a PIP2 binding here, so this structure here, it becomes an intact alpha helix, so that this becomes straightened up. So we call this straight conformation. And in this straight conformation, the comodulin made a large conformational change so that it's no longer interact with this. Okay, so we wonder whether these two conformations are related to the I state and the A state. Okay, so in order to test that, we just made a closer look at the interaction between the voltage sensor and the comodulin in the band state. We found that there is a very prominent interaction between S182 in the voltage sensor and then Y100 in the comodulin in this structure. So we made mutations of those two residues. So one of them, S182K. So we found that this mutation actually make the voltage dependence shift to the right, and also make the kinetics becomes much slower. And then we made a similar. We made another mutation in the comodulin, and it made a similar change to the channel, so that there is a shift of the GV to right, and also a slowdown of the kinetics. And then we made both mutations, and it seems there is no additional change, so that the two mutations, so it's just a mutant cycle, that the two mutations, there is no additive effect. It means that they are interacting. So basically, our mutations will just disrupt the interaction between those two residues, and presumably it will make this band conformation now becomes more straight, because there is no restriction to make them bend. And these mutations would change the current property or channel property similarly as casein Q1 plus casein U1. You see that when you only have casein 1, it's mostly the IO state, so that it is relatively faster. And then when you have casein U1, it is only AO state, so it's slower, and also the voltage dependency is shifted, just like those mutations did. So what it told us that if you disrupt the interaction in the band state, now it will straighten up, and it becomes the AO state from the IO to the AO state. Okay, so this is what we think that now this band state conformation is corresponding to this I state, and then this straight conformation is corresponding to this A state. And this is also consistent with the structure. So in Rademachelin's structure, they found that this, with PIP2 in there, they found that this channel has fully activated voltage sensor, and also the channel is like more open. It's like this state, so that, so this is from these studies, we had this conclusion or suggestion that the interaction of the comodulin with voltage sensor domain is important for the transition between the IO and the AO state. Okay, then also, if you remember that Rademachelin found that the straight conformation is in the presence of PIP2. So the PIP2 is bound in the voltage sensor, and here we found that those are the residues that will interact with this PIP2. Okay, so what does PIP2 do for that transition from the I to A state? So we made mutations of those PIP2 binding sites and try to get rid of PIP2 in certain ways. So once one mutation that is here, we found that the PIP2 would also bind to the S32 loop, the voltage sensor domain, which is exactly the same structure. Okay, binding to the same structure binding to the comodulin. So I'll be done quickly. Okay, so we made that mutation. We found that this mutation would make voltage sensor activation less, to more positive voltages. What it means is that the PIP2 binding will affect the voltage sensor activation, and vice versa. Voltage sensor activation will affect PIP2 binding. So we then made mutations of all of those PIP2 binding residues, and then we found, interestingly, it would not affect too much of the current when it is in the casing Q1 or increase the current, but it mostly will decrease and eliminate the current with when casing Q1 is expressed with casing U1. If you remember, with casing Q1, the predominant state is IO state. With casing U1, the only open state is the AO state. What it means is that if you get rid of that PIP2, you get rid of AO state, and you only increase IO state. So that would, all these data would can be summarized with a model that the channel will, during activation, will transition from resting state to I state to A state, and then the PIP2 is going to bind during here in this step that is triggered by the voltage sensor movement from the I to C. But at this binding, the PIP2 is going to compete with commodulating to turn this band conformation into the straight conformation, thereby to change the conformation from the I states to the A states. Okay, so this is the story, and I just want to say that this work was done by the talented students, mostly by Mark Zeideman, Billy Kong, and also Lu Zhao. And Jin Shi was involved in all these experiments, and we also collaborated with Monia Tarek and Lucy Delamoti's lab in using molecular dynamics simulation in our study, and Ji Sun provided some structure data with us, and Chuck Sanders helped with the structure biology, and then Peter Larson helped with our VCF recordings. And this study was supported by NIH, American Heart, and then Israel, US Bi-Nation grant. Thank you so much.
So now it's, okay, we start up there, yes.
Very nice work, Jianmin. Can you tell us more about difference in biophysical properties of intermediate and fully active state, like at the single channel level?
Single channel, yeah. So at the channel level, single channel is very hard to record. But only one lab I know in the world can do that. That's David Fadida's lab in Canada. What they do, they found that the intermediate states would have smaller single channel conductance than the fully activated state. And also, but if you look at the, just the macroscopic current between those two, the intermediate state is faster, and the voltage dependence is more left at the voltage the voltage axis, and also pharmacological properties are different. Some of the drugs will specifically act on intermediate state, and some on the fully active state, and the ion permeation are different as well.
The difference in conductance is fascinating. Do structures show any difference in a selectivity filter?
Okay, yeah, so the selectivity filter, I don't think they have sufficient resolution to show like any appreciable difference in selectivity filter, but they do show some of the in the gate area where the boundary crossing.
But there you would expect difference in open probability rather than single channel conductance.
That's true. That's true. We really don't know. So this channel is quite special. The single channel conductance is really, really small. That's why I only know that David Fadida could do that. We couldn't do that.
Yeah, fascinating. Thank you.
Yeah, thanks.
Hi. You showed the critical role of Carl moduling for the determination of IO versus AO. And I'm curious to know if the Carl moduling is calcium bound or unbound form, and if there are differences between the two.
Very good question. There are studies that using different mutations of the chemogenic binding site found that those chemogenic binding is important for the calcium binding is important for casein Q2 and 3, but less so for casein Q1. And also there was a study by 2 different labs, including Bernard Telly's lab, that when you reduce the calcium lower than 1 nanomolar, lower than 1 nanomolar, lower than 10 nanomolar, so that you start seeing some of the channel function difference, which means that in the physiological condition, it does really, because the calcium never lowers than 10 nanomolar, so that should not affect. But we are now doing, but those are looking at a different function. So we're now doing experiments trying to see the VCF with chemogenic mutations and to see if they affect these channels at all. Yeah.
Okay, last question.
You were mentioning that PIP2 also binds to the S2, S3 loop of the voltage sensor?
Yes, so S2, S3 loop will contribute 2 residues to bind to PIP2, but there are more residues around there.
So it means that in the structure you can, the loop is visible, it is resolved.
The loop is visible, yes.
Okay, and because it's bound to the PIP2. Does it also bind Carl modeling? Because you were mentioning that there is this competition between PIP2.
Right. Yeah, once PIP2 is there, it's not bound to Carl modeling, and it's a straight conformation. And the S2, S3 loop also changed the conformation like quite appreciably.
Okay.
Yeah.
That was my question. Thank you very much.
Thanks.
Okay, we have time for one last question.
Okay, thank you. So I might miss something, but I thought the PIP2 is always required for activation.
Yes.
So in this case, the Carl moduling competes with PIP2, and then make the channel in the intermediate open state. Yes. So if the PIP2 is depleted, the casein Q1 channel still can be activated.
Yes, yeah, but I'm sorry, I didn't tell the whole story, and I just mentioned that there are 2 PIP2 binding sites in this channel. So this is one of the binding sites that is in the voltage sensor domain, and there's another PIP2 binding site that is between the voltage sensor domain and the pore in that junction, and that is important for the channel to open. If you get rid of that PIP2, the channel does not open, but the voltage sensor still works. It's different from that.
Okay, thank you.
Yeah.
Thank you very much.